Lucio Mayer, your simulation of the birth of the Milky Way stimulated many discussions in online forums. Would you like to answer some of the questions that have been raised?
Sure, I'm happy to do that.
Thank you. This is the first simulation that allows reproducing the birth and evolution of a Milky Way-like galaxy. What are the main difficulties and challenges in achieving such results? Why couldn't we go to this point before?
There are mainly two difficulties in trying to simulate the formation of a galaxy. And one of them is the fact that it's a very complex process. We know it because we know the basic processes that are actually taking part into the galaxy formation. And they involve being able to model in a computer simulation a wide range of scales that go from much larger than a galaxy itself, so cosmological scales, sometimes millions of times larger than a single galaxy, to scales that are much smaller than the galaxy itself, where, for example, stars form in clouds that are only 100 or 1,000 times smaller than the entire galaxy. So it's a big challenge because of this large range of scales. And each scale has different processes that matter. For example, on large scales, gravity is really the dominant process. But as we go to smaller and smaller scales, there are other processes related to the radiation, related to stellar explosions and stellar evolution that are actually playing an even more important role than gravity itself. And putting together all these different processes and all these different scales in the same model has always been a major challenge. I think the progress has been possible in two ways, and it's also fair to say that it's been the result of many little steps that Haas and other people, other groups have done in the meantime. And these two ways are mostly being able to capture more and more physical scales in the same simulation, which is strictly related to being able to compute faster and faster and larger. And so the supercomputing evolution has been crucial to this, and at the same time also the evolution of the codes that we use to compute on big machines like the Cray at Mano. And the second aspect, which is equally important, is being able to recognize what are really the most important ingredients, the most important processes that have to be included in this model, because there's always some approximation that has to be done. It's impossible to include all the physics, all the scales. There's always an approximation, and it's important to recognize what can be done and what cannot be done, and figuring out really what are the crucial ingredients has been why we were able now to simulate realistically the formation of a galaxy like the Milky Way. And one of these important ingredients, which is crucial in our result, is the ability to indicate where stars are forming and where they explode as supernovae. So how they release the energy, to which volume, essentially, around them they are able to shed the energy and produce a strong effect on what we call the thermodynamics, or the equilibrium structure of the galaxy in its subcomponents. So this has been really the major ingredient that was not possible to include properly before, and now it's included in the models. And so these explosions of supernovae now put together in the model in the right place. Stars explode really in the regions where the density is high enough for them to be born in the first place. This density was not possible to reach in previous model. Now generates this strong effect of explosions that drives out some of the matter, some of the baryonic matter, the ordinary matter, especially the matter that has low angular momentum, rotates with very low rotation speed. And so the end result is a galaxy that has the right amount of baryons at the center, and so does not suffer anymore from this overly massive bulge. Main reason is, as I said, because we are able to expel a fraction of this mass through these supernova explosions.
Many viewers ask, how can we be confident that this is the way things actually took place? Can we compare to real objects that we observe in the sky?
Yes, we do. And actually, the reason why before we knew that the results of simulations were wrong was exactly because we could compare with real objects. We could always find, we could clearly demonstrate that the galaxies coming out of the simulations were not like real galaxies. Typical spiral galaxies have a dominant rotating disk of gas and stars and a small centrally concentrated component that we call the bulge, which is mostly stellar. Whereas in the simulations, it was the opposite result. coming out. So the galaxies had typically a bulge that was dominating in mass over the disk, or was at least comparable. These type of galaxies do exist because there are galaxies that have big bulges, but they are not the typical spiral galaxies. They're actually an exception rather than the rule. And so now we get the rule. And now, of course, the next questions will be to be able to show that we can also still get the exception. This is part of what we have to do next, being able to extend the model to other types of galaxies as well. We know already, again, driven by the knowledge of real galaxies, that we can reproduce with the same model also small galaxies called dwarf galaxies. This was a work that we published last year. And for dwarf galaxies, we used exactly the same recipe, the same modeling. And we were able to reproduce a realistic data set, meaning that we really compared with real data set. We teamed up with observational groups, and they compared using their own tools to analyze galaxies, the real galaxies in the real universe. They used the same tools to analyze our galaxies, and they found very similar results to the galaxies that they typically observe. This exercise that we did for dwarf galaxies, we will do also for this new work of the spiral galaxies. We are already doing that as I speak. And this is the best way to compare with real galaxies and be able to conclude that what we produce is a good replica. Because if you give the observers their analysis to do, they will do it exactly in the same way, which is not what we do normally. And so if they come out with the same result that they would typically get with the real galaxies, then it's even more a strong evidence that we are doing the right thing.
In your paper, you describe the importance of dark matter in the creation of our galaxy. What is dark matter, and which are the evidences that it exists?
Well, again, first of all, dark matter is just matter that cannot emit light. So you only determine that it exists based on this gravitational effect that it has on the surrounding matter. And one way to measure the gravitational effect, the fact that there is mass that you cannot see, is to measure the motion of stars and gas in a galaxy. This is actually the original discovery of dark matter. In the 60s and 70s, people who were measuring the rotational speed of galaxies started to realize that there was not enough visible matter to justify the high rotation speeds that they were measuring. And so that's how astronomers started to think that there probably was something additional that could not be seen. Even earlier than that, more speculative in a sense, more far from detailed data analysis, but still correct, was what Zwicky thought in the 30s and 40s, where he realized that to keep these big ensembles of galaxies called galaxy clusters together, you would need a much bigger mass that you could see in galaxies. So this is probably even earlier than observations of rotations of galaxies, the first thought about the existence of dark matter. But rotations of galaxies were really proving that, by numbers, that it was impossible to justify the speeds that were measured without an additional component. Then after that, there were a lot of other pieces of evidence that were put together to justify what we call today the standard model for structure formation, for cosmic structure formation. In this model, not only we say that there is dark matter, we say that there is a particular type of dark matter that dominates mass in the universe, which is called a cold dark matter component. Without going into details, what it means that it's a type of dark matter that only has a gravitational effect on everything, doesn't have any interaction through electromagnetic waves or through other common interaction like nuclear forces, for example. So it's different from ordinary matter because it does not partake to the other forces, but only to gravity. And by postulating this type of dark matter, without even knowing which particles actually are making it up, but just postulating the behavior, we are now able to explain a lot of things. We're able to explain the distribution of galaxies on very large scales, on millions of megaparsecs, so on scales enormously much bigger than our galaxy. And now, which was an open problem before, it seems that we are also able to explain how galaxies form with the same model.
Many viewers complain about the low resolution of the movie. Wouldn't it have been possible to produce a high-definition movie?
Yes, it would have been possible. It's more a matter of amount of data that is produced as we run the simulation. So dumping the frames as we do in real time, because we dump the frames as the simulation runs, actually takes memory out of the whole process. And so we will try to do something more efficient so that we can get higher resolution frames without having to increase the burden in the memory that we use. So it's certainly something that we could do in the future.
The cost of the simulation in terms of computing system, power, and work is very high. What's the return of this effort and its impact on society?
I think that there is a very important return. Maybe I'm biased because I am, of course, very deeply involved in this type of research. But in general, I think as for any field of physics, which is the most fundamental science of all, extending our knowledge is the main driver of progress in humanity, has been the main driver of progress in humanity. I think if you think of what is life of human beings today, with all the technology that we have, but even if you go just a century ago, with the birth of electricity at disposal of everyone, it changed completely the society. Then internet came, the computers came. All this comes from physics, comes from the knowledge of nature, comes from being able to understand the physical laws, and being able to say that we are approaching a better and better understanding of our universe in a certain paradigm. This particular model, which we call the cold dark matter model, is also another way to understand the physical laws better and better. And who knows what progress can bring to humanity in the future. I can't predict it now, but certainly it is clear that if you look at history, any progress in physics has led to progress in technology later on, and progress in the life of people at some even later stage.
And in this case, what are the main challenges in astrophysics currently studied with the help of supercomputers?
There are many. Right now, astrophysics, like other fields of science like climate modeling or molecular biology, has become a field that really relies a lot on simulations in order to make significant progress in concert with astronomical observations. This is really the synergy that is bringing most of the new understanding and the new knowledge in the last decade or so. The synergy between observations and simulations. And galaxy formation is just one of the main challenges, but there are many others. For example, one that is very fascinating, very attractive also for people who are not working in the field, is understanding the origin of planets, and then related to that, of course, the origin of life. And this is where also astrophysics meets with astrobiology and biology more in general. And the formation of planets is also an active field of research right now, and is becoming more and more heavily dominated by computer simulations and also observations, of course. And it's even more in an infancy than galaxy formation. I think it's more like galaxy formation was 15 or 20 years ago, because here now we have a fundamental model, we know it works. In planet formation, we are still debating about which is the right main model to form planets. So there are still different theories that are competing, and each of them has good and bad things to say. And so I think in the next decade there will be an explosion of computer simulations in planet formation, even more than it is now.
And what is still missing in your model? How will you improve it in the future?
Well, there are still many things that are missing in our model, especially many things that are still treated in a very simplified way. Because, as I said, despite the success, we are still limited by the resolution that we can reach now. We can only get down to scales of hundreds of parsecs, so we can capture only the biggest gas clouds where stars form in the galaxy. But stars form in clouds with a range of masses down to 100 times smaller than we can resolve in the simulation. And so we are still doing some leap of faith in assigning stars to a place in the galaxy in our model. And also the way we treat the explosion of supernovae is still a phenomenological way, because we cannot really resolve a single explosion. So we treat more the collective effect of many explosions, the way we think this effect should actually happen in nature. So all these processes eventually would have to be directly simulated, rather than simulated in a phenomenological way, to confirm further that our model is really correct. And then we miss completely some ingredients that are being put now in the new series of simulations. For example, the presence of a black hole at the center of a galaxy. We know that there are black holes at the centers of all massive galaxies, including our Milky Way. And here is not present in the simulations. There is the idea that black holes have an important effect on the development of galaxies themselves because they can release also energy through the accretion of matter. When the matter accretes onto black holes, it becomes very hot, emits radiation, and this radiation leaks out and has an effect on the entire galaxy. This is the idea. There is a lot of work being done in this direction, but there is no clear understanding of how big is the impact of black holes on galaxies. Starting from our model is quite interesting now to put in black holes, because what we showed is that we can produce a galaxy that looks right without including a black hole at the center, in a sense. So if we are right, we expect that for massive spiral galaxies like our own Milky Way, the effect of the black hole cannot be dramatic, because otherwise it would change a result that seems now correct. But it might have been more important for much bigger galaxies, which have also much bigger black holes. We know that from observations. We know that simulating big galaxies with this technique is going to be a major challenge, because you need to capture even more scales, because the galaxy is bigger, but the clouds in the galaxies are, or can be, as small as the clouds in a galaxy like the Milky Way. And so it's going to be a much bigger challenge. And I have the impression that black holes will matter a lot for these big galaxies. I think most astronomers will probably think in the same way. But we are now starting a repeat of ERIS with black holes to see, if not the effect on the galaxy, certainly how the interaction between the galaxies and the black hole develops during cosmic time. Black holes themselves have to grow. We think that they start small and they grow bigger. We don't know exactly how small they start. There are different theories about that. Our group believes that they start not so small, but they still need to grow to the sizes that they are at the present time. So understanding how they grow, even if they don't have a big effect on the galaxy, is important to understand black holes themselves. And so this is why the study of including black holes in the simulations is two important applications. One is understanding even better galaxy formation. The other one is really understanding black holes themselves. And the reason why understanding black holes themselves is important is because they can open a new window on the observations of our entire universe. When they form, if they form very big and they collapse very fast, or if they merge with another black hole, they can emit gravitational waves, which have never been detected but are predicted by Einstein's theory of general relativity. This is one of the holy grails of fundamental physics and astronomy of the future. And in order to understand how we can detect them, we need to understand how they evolve. And so understanding this in the simulation is a way to prepare for these new experiments that will be done in the future to detect gravitational waves. Essentially, there is no understanding of which signal will come from which part of the universe at which time back in the earlier part of the universe. And with the new simulation that we are planning, we hope to be able to at least give guidelines of what one should look for, essentially, for this new gravitational waves experiment.
You stopped your simulation after 13 billions of years. What will happen if you would continue? What will happen in the end?
Well, I think in the particular galaxy we are simulating, it will probably look a bit boring, because we chose on purpose a galaxy that forms in a fairly low density region of the universe. So we call it a fairly isolated galaxy, meaning that it doesn't live in a region with many other galaxies nearby. And so as the simulation progresses, because it is in a relatively low density region, it will encounter fewer and fewer galaxies. You see the movie that has been shown also on YouTube typically shows that there are many galaxies interacting with the main galaxy. And these they bring gas, they bring material that lets the galaxy grow. As the galaxy progresses its evolution even beyond our ending time, because the universe keeps expanding, and because it lives in a fairly low density region, nothing interesting will happen. At some point, it will not be close enough to any other source of matter to become bigger and bigger as it is now. And so it will start to evolve more or less without changing much in size and mass. And so it's going to be a fairly boring evolution as we progress in time. And we simulated a cluster of galaxies where there are many, many galaxies nearby. There will be more and more action taking place for many more billions of years, many more encounters between galaxies, many more exchanges of matter. But eventually, because in this model that we call the standard model, there is a cosmological constant that drives an acceleration in the expansion of the universe, eventually even the galaxies that were born in regions that were fairly dense will become fairly isolated, because this accelerated expansion, this unknown source of energy, which we call dark energy, will win over anything else. So the energy density will become much, much greater than the energy density of standard matter and dark matter. And so all the galaxies in the end will look very isolated as this one, and will evolve in a sort of empty region of the universe without accreting anymore. So if you want, this is an example of what a typical galaxy will become, and at some point in the future, eventually, independently of how it formed, eventually all galaxies will become isolated like this.
And after some additional billions of years, the light will go off?
There will not, yeah, it will be a very boring universe, because at some point, you know, this galaxy and any other galaxy will be so distant from the neighbor that it will not even see light from it. So the universe will become darker and darker and darker and darker. So not only there will be little action taking place, but also it will become a darker and darker universe. Not a nice place to look at, not a nice sky to watch during a nice night.
Okay, Lucio Mayer, thank you. I'm happy to be here and now with the light, and thank you for answering our questions.
Thank you very much.